Awesome. Well, thank you so much, Levitra, and thanks everyone for being here and being part of this webinar series focused on bulk power system connected inverter-based resources. We're really excited to be delivering this 11-part webinar series where we're going to be covering everything from the high-level basics of inverter-based technology and NERC strategy, risk mitigation strategy for tackling the changing resource mix and the new technology we have in the system. Diving in then deeper into the various facets of reliability with growing levels of inverter-based resources. So first, I want to start with a couple logistics items before we get underway. Our top priority and the main thing I want to touch on is please ask a lot of questions. Use the Q&A feature of WebEx. We have Q&A sessions at the end of each panel I'll talk about here in a second, but we probably won't get to all the questions. But what we are going to do is put together a FAQ document after the webinar series, and we'll post that publicly. And then we're going to use the feedback, the questions, the comments that we get back through the Q&A to help drive our IBR initiatives moving forward. So please share your thoughts, share your questions, ask a lot of questions. That's a great way you can engage with us along the way. All the webinars will be recorded and posted online with the presentations. Those will probably go up after the webinar series is complete, so stay tuned for that, but I know we always get a lot of questions on that. All the webinars will be posted along with the slides. So the way we're going to run each webinar was actually inspired from our February technical session at the MRC board meetings. We've got a panel of speakers consisting of NERC staff, but also predominantly industry stakeholders. And we're really going to focus in and hit the high points. We don't have a lot of time. We want to be respectful of everyone's time. And so we're going to get right to the point and share the message that we feel needs to be shared with the industry. We're going to hear from some experts in various areas of the IBR risk mitigation. And after each set of panelists, we'll have a short Q&A session as time permits. So like I mentioned, we'll be covering a very wide range of complex topics, but we've really tried to craft the webinar series to be digestible for a wide range of stakeholder groups around the industry. So hopefully everyone can take away something from the webinar series here. Like I mentioned, we're covering basics at the beginning down to the meat of the challenges that we're facing and the full spectrum in between. So if you're new to the industry or you haven't been following NERC's IBR activities over the last 6, 7, 8 years now, I want to just briefly share what we've been up to. We've published 8 disturbance reports covering over a dozen widespread inverter-based resource loss events. Each one was unexpected and abnormal, and we've learned something from each event. We've issued 3 level 2 NERC alerts. We've published numerous reliability guidelines, technical reports, white papers, assessments, studies, etc. We put on a ton of workshops and webinars with our industry stakeholders and partners like NATF, EPRI, etc. And we've also really tried to make a concerted outreach effort with industry partners as well, registered entities who have reached out wanting more information, SIA, and numerous other entities. And now we have, I believe, 9 standards projects currently underway, making enhancements to the NERC standards to keep pace with the rapid change that's upon us. So I really just wanted to highlight, bring it back to our shared mission, the effective and efficient reduction of risks to reliability and security of the bulk power system. And under this, rapidly transforming grid that we have upon us, we must adapt. We have to think differently than we have in the past and sort of challenge the status quo to some extent. And that requires us to innovate, but more importantly, to collaborate and to be proactive and ask these big questions that we probably haven't had to ask in the past. And really, we have to do all these things because we don't have any other option, right? The grid transformation is here. It's upon us now. It's happening now. And it's happening at an order of magnitude faster than it ever has in the history of the power system. And we're all very lucky and fortunate to get to be part of all this change. So it brought me back to a Steve Jobs quote, the ones who are crazy enough to think they can change the world are the ones who do. So with that, I just wanted to welcome everyone again, and I would like to introduce our President and CEO of NERC, Jim Robb, who's going to share his perspectives on where we are and where we're headed as an industry around this IBR risk mitigation topic. So I'll turn it over to you, Jim.
Well, thank you, Ryan. And I really want to thank you and the team at NERC and all the stakeholders who are going to support us in pulling together this series on inverter-based resources. I think it's a tremendous initiative. One of the things I've come to appreciate over the last several months is that we all enter this conversation with different points of knowledge as to how inverters work, how they integrate with the grid, the opportunities we have in front of them to help inverters contribute more positively towards the reliability of the grid, and importantly, not allow them to play roles that degrade and detract from the reliability of the grid. You know, we've seen dating back to 2016 a series of events which have their roots in how inverters perform during grid disturbances, and frequently fairly minor disturbances that tend to create a reaction of the inverters to trip offline and take modest performance issues on the grid and amplify them into major events. The most significant of which was last year in Odessa, Texas, when a simple disturbance on the grid that would have been cleared automatically prompted about 1,700 megawatts of inverter-based resource to trip off the grid, which also then created triggered 800 megawatts of conventional generation to trip off the grid. And so with something that should have cleared itself, we ended up having a 2.5 gigawatt loss of generation and almost put ERCOT into an EEA3 situation. Clearly, this is something that we need to get our collective heads around and figure out how we work with inverters to contribute to reliability. And there's great reason for doing this. They are coming onto the grid at enormous numbers. You'll see in our summer assessment that we published earlier this year, almost 20 gigawatts of new generation, solar-based generation, was added to the grid last year, and it's making a really positive difference to the performance of the grid. Combined with batteries, we're seeing how batteries made a very positive impact during the heat wave that California had last Labor Day. But these resources that integrate with inverters also need to be able to work effectively with the rest of the grid during all circumstances, and that's what this uh, webinar series is all about. It's really important that we find ways to streamline the interconnection queue, and I understand all of the concern around the length of time it takes to interconnect resources, and we agree that those should be shortened as much as practical. However, we can't take shortcuts. One of the things we're very hung up on is making sure that these resources are properly modeled, and that the control room operators who have to dispatch the system with increasing numbers of inverter-based resources on the system will know how they're going to behave during all sorts of grid situations. So it's important that we get this right. Inverter-based resources clearly are the future of the electric grid. There's no question in my mind that we're going to continue to see advancements in battery technology that's going to be so important for integrating variable resources onto the grid at scale. And the interconnection queues that we see across the country clearly show that the interest of investors in generation is highly skewed towards wind, solar, and battery systems, all of which integrate into the grid through an inverter. So this is really God's work in figuring this out so that the grid that we leave behind for our grandchildren will perform at the level that we've come to expect the grid today, right? Where we have extraordinary levels of reliability, 24 hours a day, 7 days a week, 52 weeks a year. And that's what this is all about. And grid reliability is increasingly important as we continue to push to electrify more and more end uses of energy, whether it's through the transportation sector, the space heating sector, buildings, etc. Our tolerance for even short duration outages is going to decline very rapidly to zero or below. So this is really important that we get this right. I really appreciate you all listening in today and in the future webinars. And I know you'll find this a good investment of time, irrespective of what your entry point is from a standpoint of knowledge of how these resources work. So thank you for being here. And Ryan, with that, I'll turn it back to you.
All right, thank you so much, Jim. I want to just now introduce Alex Shattuck, who is a senior engineer in our engineering team, who's going to really be the MC and the orchestrator of these webinar series. He's been the brains of the operation and has put the whole thing together. So hats off to you, Alex, for putting on this great event. We've got great turnout and excited to see it all play out here. Alex has got a tremendous amount of experience across a wide spectrum of IBR risk issues, worked at a equipment manufacturer, consultant, and ISO RTO, and has really been involved in all facets of the IBR risk mitigation strategy. He's now coordinating our inverter-based resource performance subcommittee. So if you're interested in participating in that group, feel free to reach out to Alex or myself. And I guess without further ado, I will turn it over to you, Alex, to kick us off on webinar number 1.
In a undesired way with the controller of another inverter. We also need to think about, are these devices resilient to faults? How will they respond if the voltage suddenly goes low, or the frequency suddenly changes quickly, or there's a jump in the phase angle of the grid? Will they remain online and respond in a positive way, or will they trip or cease their output or do some other behavior? All these things are really important to consider. It's also important to think about, how will the power system as a whole be resilient to loss of generation events or faults when it is dominated by inverter-based resources? And of course, that will be dictated by exactly how those inverter-based resources are controlled. There's also another issue with the system strength of the power system. In other words, how strong is the voltage of the power system at a given location? These conventional inverters, which are, as I mentioned on the previous slide, tracking the voltage at their terminals and synchronizing with that, basically need that strong voltage to synchronize to, or they can become unstable. And so as you get more and more of them on the system, that can introduce system-wide stability issues or local stability issues that need to be considered. Of course, there's also issues with scheduling and dispatch of these resources, scheduling of reserves. Typically, inverter-based resources historically haven't been operated with reserves, but they certainly can be. Does that need to be incorporated into power system operations? Some people have talked about, do we need to schedule the inertia of the power systems, that we have enough inertia all the time or enough synchronous machines all the time? I'm not necessarily saying that we do, but that's one potential solution that's been applied in some places. Do we put constraints on the maximum levels of inverter-based resources to ensure stability of the power system? That's also been applied in some cases, but there may be some ways around that as well. If we have lots of these resources, how do we black start the system? I mentioned earlier that also protection can be a concern, since they have different characteristics for faults. Ride through is, of course, a big concern that we've seen lots of evidence of already on the system. And then, of course, we need accurate models of these devices. If we want to know how the system is going to perform with lots of wind and solar and batteries, we need to be able to model how the system responds to different faults in different present and future scenarios. And I'll talk about a little bit on a future slide that modeling actually needs a little bit more detail for an inverter-based resource than it does for a synchronous machine. And of course, this seems like it should go without saying, but it's been a big challenge in industry so far. The models of the inverter-based resources need to actually match the behavior of the resources themselves. Seems like an obvious thing to say, but that's actually one of the biggest challenges in industry today. Next slide. Oh, I realized I thought I had my video on, but it maybe went off, or anyway. Okay, so I'm going to talk a little bit about that modeling topic that I just mentioned. So because these resources are responding to the actual sinusoidal voltage waveform at their terminals, in order to accurately model all of their behavior, we need to actually model that sinusoidal waveform. And that's not modeled in the typical stability tools that our people use today, things like positive sequence phasor domain simulation tools like your PSSEs, your PSLFs, your TSATs. These tools model the effectively phasor of the grid, or the root mean square magnitude and phase of the voltage at different locations, but they don't model the actual sinusoid, which is what the inverter responds to. And the effect of that is that they can miss some of the dynamics of the power system depending on the frequency or the speed of the interaction you're concerned about. So dynamics of the system that go faster than a few changes per second or a few hertz can be missed by those existing tools. And we need to actually use something called electromagnetic transient simulations, or EMT simulations, which means tools like PSCAD or EMTP or others that can actually simulate those AC waveforms and simulate the full details of how the inverters respond to those dynamically in the system. One of the big challenges with those tools, though, is that they're orders of magnitude slower than phasor domain tools because they're more detailed. They need smaller time steps. The time steps are on the order of microseconds instead of milliseconds. And the level of detail in the controls is quite a bit more detailed. And so to be able to capture that, we need much more detailed models that for a large power system might take many hours or even days to run, not to mention the time to develop and validate. So this is a pretty big challenge the industry is facing today. We're trying to figure out, you know, how to address that challenge. Existing tools are being improved. There's research on how to make new tools. And so we're trying to figure that out. One of the approaches is to model parts of the system in EMT detail and other parts in less detail, which can sort of help speed up the simulation time. For all this to work, of course, again, we need good models of what the inverter-based resources are going to do. For resources on the transmission system, that means submitting actual detailed models of every plant that's submitted, making sure those are at least collected, if not studied. For those on the distribution system, it needs to be an aggregate model because there's so many thousands of them that it's actually intractable to model them all. So we need to figure out ways to model those in aggregate to figure out how the transmission system stability will be affected by these new resources. Anyway, that's a basic overview of something that I'm sure other presenters will talk about in much more detail, just to note that it's a challenge that we're facing. Next slide.
It's only got 5 minutes left.
Sounds good. So just a few potential solutions. Next slide. Okay. So a few things that are important for inverter resources to do in order to make sure the power system is stable would be to actually reliably ride through transient events like faults and losses of generation and things like that. And then during those events, they could actually provide voltage support and frequency support. That frequency support could be provided on a range of timescales, including all the way down to the inertial timescale, conceivably, depending on how the inverters are controlled. Of course, again, we need models that accurately reflect how the inverter-based resources are behaving. And a lot of that can be accomplished through standards, including various NERC standards that are trying to tackle this issue, as well as IEEE standards that are in various phases of being adopted throughout industry. For example, IEEE 1547-2018 tries to tackle many of these issues for distribution-connected IBRs, and IEEE 2800, which was just published last year, tries to tackle a lot of these things for transmission-connected IBRs. Next slide. Okay. I'm going to just give a quick overview of a topic that you're going to hear more about again as we get more and more of these inverter-based resources. I mentioned that they're just trying to inject current. Well, there's actually another way of doing it. But first, I want to try and describe what the issue is that we're trying to address here. This is an interesting slide made by a student who worked with me a couple of years ago. He made up this analogy of grid forming resources as being regular bicycles, grid following resources as being the ride behind bicycle, and the power being the bears. And you can see that, you can kind of imagine that as you get more and more grid following resources, the bicycle becomes less and less stable until eventually you crash. Basically, that's a way of saying we need to have enough grid forming in the system for it to be stable. Next slide. It's actually possible to make an inverter-based resource be grid forming, and this is something that's been done for a long time in off-grid systems, but the new thing that's come out in the last few years is to make inverter-based resources be grid forming in parallel with the rest of the power system. In other words, and rather than acting like a current source, they can act like a voltage source, help with the system strength. They're not necessarily going to solve all the problems I talked about earlier, but they can probably help with at least the stability issue, some of the stability issues I talked about earlier. This is a new technology that's basically available now for battery systems, and maybe available in the future for things like wind and PV systems. So this might be able to help with some of this issue as well. NREL and NERC and many others have put out some recent publications on this topic. Next slide. And you actually have now some experience with inverter-based resources on the actual power system. There's several in the US, there's a few in Australia, but the experience is pretty limited. I would say it's a promising technology, but we have a ways to go before we actually fully leverage it. One of the biggest steps is actually getting more of it out there so that we can get more experience with it, and see more of the benefits that we hope that we'll be able to see. Of course, as with any inverter-based resources, ride through is still an issue that we need to make sure of. And then I also kind of want to caution you that this word grid forming has become a bit of a buzzword. You'll hear it used in different ways. What I'm trying to say here is that it's useful to have inverter-based resources that look like voltage sources, and that's what I mean by grid forming. That's pretty well aligned with the definition in a NERC document that came out recently, that you can see on the screen here. Next slide. All right, so just to conclude, summarize some of the main points. We're getting more and more of these IBRs in the power system. At times, they're going to be the dominant resources in the system. This introduces a bunch of challenges that are not insurmountable, but that we need to plan for, and we need to operate maybe in different ways than we used to operate. These IBRs are going to need to have ride through. Most importantly, they'll also need to support system voltage and frequency, and they'll need to provide accurate models. A lot of that can be addressed through things like IEEE standards and NERC standards compliance. We need electromagnetic transient models of these, especially the transmission connected ones, to make sure that they can be modeled accurately. And those models actually need to match the behavior of the plants and the devices, which is, of course, is another challenge. And I think another point I'd like to make is, as we install these inverter-based resources, they're going to be on the system for 20 or 30 years. So it's pretty important to think about the capabilities we want them to have, not just today, but in 20 or 30 years across the lifetime of their operation, so that we have what we need and don't have to end up retrofitting them, which can be costly and difficult to do. And as a final point, for really high levels of inverter-based resources, which we almost certainly are going to get to, we already are getting to in some areas, some of those probably will need to be grid forming. There are other solutions. You could put a whole bunch of synchronous condensers out there. So I'm not saying this is the only solution, nor am I saying it's going to solve all the problems, but it's probably a good part of the solution. So I think with that, we can wrap up, and happy to take any questions.
Thanks, Andy. We're going to take questions together, you and I, at the end. So
sounds good.
What I'll do is, we're actually pretty much right on time. So what I'll do right now is I'll go over kind of our NERC IBR strategy, just as an overview and kind of what we're doing and why this webinar series is happening, as well as give some details on what else is coming. Andy mentioned a couple times there will be topics on, more detail on some of his topics later on, and we have lots of presenters from the industry, and we'll go through that a little bit throughout the slides here. And then we'll take maybe 5-10 minutes at the end for some questions. So maybe I have to cut myself off at the end. We'll see if I get myself the hook here. But to get started, this is NERC's IBR strategy. So, what is an IBR strategy? It's basically NERC's, strategy for trying to assess the current risks with inverter-based resources as we're going through this energy transition, and prioritizing those risks and tackling them, in various different ways with either standards or outreach or webinars and things like that. So if we start with just the far left pillar here, a big piece of the IBR strategy, the first pillar is our risk analysis. So this is the kind of process and piece of NERC that spits out the NERC disturbance reports. They do a lot of detailed analysis on the events and what's going on and why they happened, as well as give a lot of good recommendations, both for NERC, from NERC to NERC, recommendations for standards and things like that, and also recommendations for industry, things that they can do perhaps to increase their BPS reliability. Included in the risk analysis is NERC alerts, and you all have probably seen a lot of the announcements and the release of our inverter-based resource performance alert in March. That comes from things like disturbance reports and event analysis. If we see things that seem to be systemic or are happening very often, that's where an alert can come in, where we can give some recommendations to maybe stop these things from happening as frequently, and to get some data back so we can more understand what the current condition is, and what we can do to get the BPS reliability a little bit higher. And then a little bit smaller than an alert. So like the Odessa report was an alert. The Odessa report was a disturbance report. We have something called the lessons learned, which is like a mini disturbance report. If there's just something, an event that was just one facility, or a couple of facilities with very mundane type causes of disturbance, that would be something like a lessons learned document. And there's a couple of those coming as well, along with a couple other disturbance reports we'll cover on the next slide. But the second pillar is, we're trying to focus on improving the interconnection process. What that means is, both from, market participants, planning coordinators, planning or transmission providers, making sure that those requirements for the interconnection process are improved and are stringent and can help close all of the gaps, kind of like Andy mentioned before, specifically maybe in the modeling portion and the site data pieces of the interconnection process, trying to improve the process so that there's requirements and things to make sure that all the studies are being done accurately and correctly with accurate inputs. So improving the interconnection process comes through a lot of different avenues. We could improve the the FERC GIA or generation interconnection process. We can enhance interconnection requirements. So those folks who are currently making interconnection requirements, posting them under our FAC standards, those could be enhanced. There's a lot of good examples around North America now where new interconnection process requirements are coming out that seem very promising as far as trying to raise the bar and raise the floor of the data and things that get used throughout the process. That also incorporates modeling and study improvements. NERC's also going to release a little bit of an updated model guidance document that looks a little bit and will act a little bit like the previous NERC acceptable model list. That'll be just a NERC guidance modeling document that should be posted sometime soon. And that's in all these things. Also, I think Andy mentioned it as well. We do also support IEEE 2800 2022 and some of the other IEEE standards, because those standards were a massive industry effort. They included a lot of very smart people and a lot of stringent balloting and consensus to come up with those requirements. They can be a really good base for improving your own you being TPs or PCs interconnection requirements. We also do best practices in education, kind of industry outreach. We do reliability guidelines through either our task forces or through IRPS webinars and workshops like this one, outreach and engagement, I guess, also like this one, and trying to figure out what's coming by discussing and having meetings with industry to see if there's any emerging reliability risks. With all these things, this first three pillars, a lot of it is things other places are doing, maybe your requirements or us doing outreach and analyzing events. But what really has to happen also to help improve this reliability for the BPS through the IBR strategy is regulatory enhancements. So those could be NERC standards projects. There's a bunch of those currently working in parallel. There's IBR registration, as we were just ordered by FERC, and then inverter-specific requirements and standards, either as a standalone standard or maybe language revisions to some older standards that were written and balloted and approved prior to a large penetration of IBR, where some of the language might not mesh exactly with what's going on in IBR when compared to synchronous machines. So to go back to what's happened and what's driving things moving forward is we keep seeing and we keep analyzing these disturbances. We had 2 disturbances in Odessa, basically the same facilities tripped offline for a very similar event. And we presented on that a couple times, but in addition to those, there's another BESS-related event in California. There's a wind event in Texas, and another solar PV event in Utah. So even with Odessa's just being published, I think it's in December, we are still working on the disturbances and still analyzing disturbances. And so what that means is we have to have some actions and take some actions because these disturbances are happening. So what have we done and what are we going to do is, we're elevating the inverter risk issues within the ERO enterprise. So we're saying IBR related things should be prioritized a little bit more since they are an emerging, reliability risk, relatively new technology compared to spinning machines. We're also asking industry to take immediate action to enhance the local interconnection requirements. We've said it in a couple different avenues. Again, NERC standards development practices, development activities. We're doing just off the top of get my head, or I guess these slides or these bullets here is there's a new PR24 comprehensive breakthrough standard, and then a couple standards, a standard project, and then a couple activities, including an EMT task force for specific EMT modeling and practices and disturbance modeling and planning assessments and things like that. There's a lot of standards enhancements coming currently being operated upon at the NERC level to try to give some guidance and give some requirements for being reliable. I did mention also we did release a level 2 NERC alert. So what this was it gave a lot of recommendations, and we're asking for data back, and that's due June 30th. And once we get that data, we'll parse all of it and kind of understand the extent and condition of what's going on and what's out there in the field. We'll be able to make some conclusions and actions coming out of that relatively soon. So in addition to that, we also see a really big need for improving the commissioning practices. That's connecting your facility to the grid. We see a lot of gaps, like Andy mentioned, between plant performance and models. A big part of that is that they don't usually get aligned during the commissioning process. So you might have a situation where planning folks do all of the studies with the model, and they never speak to the construction folks, and then they both kind of happen in parallel, but they don't ever get matched. And then we have we basically have an unknown on the grid. We're also doing, we also had a FERC NOPR. They have ordered us to come up with a work plan for registering IBR resources, because smaller IBR resources, not currently BES, do have a material impact with in the aggregate, right? A lot of small inverter-based resources can have a large BPS effect as far as reliability and performance is concerned, and also driven by the disturbances and some other things, like Ryan had mentioned, the presentation at our board meeting. This NERC webinar series is coming out of those as well. So in addition to the webinar series, there's 2 shorter, one's very short and one's pretty short, documents that we're going to publish in the coming weeks. And one of them is kind of an IBR basics. So if you're participating in this, or you're participating in the IRPS, and your management asks, what are you doing for IBR and why are you doing it? This is a good one for upper management or people who want a quick summary of IBR basics in the US. So this has it's only a couple pages long. It addresses some frequently asked questions that we get from industry. It has some definitions for terms. It has a little bit of information on difference between inverter-based and synchronous resources, and then some reliability best practices when thinking about IBR. The follow-up to that is more detailed, quite a bit longer document. We call it the IBR primer document, and it's much more detailed on a lot of the topics that the basics document covered. There's a good write-up on grid transformation, moving to IBR. There's a big expansion upon the difference between inverter-based resources and synchronous machines, and why, and the effect on the reliability. It covers, the nuance between IBR at the grid level and distributed energy resources at the, obviously, the distribution level, both at IBR, but very different. And then it also discusses, what reliability risks there are currently for IBR at high penetration. So be on the lookout for those two things as well. We'll post them with the webinar materials when those are released, and you also get kind of the regular NERC announcement when those get posted. But be on the lookout for those. They're kind of supplemental information for this webinar series. They'll help a lot. Getting your base information up and sharing it maybe inside your organization for kind of a good summary, high level summary of what we're doing right now. So with that, I've got a couple more minutes before we take questions. This is the number one of the webinar series. There's 11 of them total. The last one, number 11, will be kind of like this one. It'll be all NERC presenters with summarizing what we've learned, what we're doing, and what's coming next. This webinar series, like Ryan had mentioned, is supposed to be like a one-stop shop for figuring out or finding out what is happening, right? What's going on? What problems have we been seeing? What are the solutions? And kind of what's the industry up to? So we have 20 non-NERC presenters throughout these, nine-ish, including this one, more technical presentations or series from 20 different organizations. So there's a pretty good cross-section of the industry. We have folks from OEMs and TPs and PCs and consultants and other regional entities. There's a really good mix of folks. So what we got here is this is a more detailed lineup. This just shows all the organizations and the team members who are presenting. The topics in the topic column are they're not the titles of the presentation, they're just kind of like high level ideas of what we're going to cover in these sessions. So if you're wondering which one you want to participate, if you can't make all of them, you want to pick one or two to join, this would be a good place to look. You can always email me or and see more detail on any of these. So like Andy had said, we're going to have a bunch of more detailed sessions, and real quickly, I'll just list them off, and then we'll take questions. But the next one on Thursday is kind of our NERC disturbance reports and what goes into them. So we have folks from NERC and the industry talking about what goes into them and what happens. From those, we have a webinar on inverter-based performance issues. So what's happening and what performance issues do you see with IBR in your current systems? There's a session for interconnection requirements, how to establish and enhance those. There'd be two sessions on modeling. Modeling is kind of a big topic right now. So the first one is, how models get improved, how they get turned from an OEM model into facility model, and then some experience in different regions for establishing and meeting model requirements. And then the second modeling one will be ERCOT's model quality assessment, a modeling presentation from Vestas, and some information on supporting those models internationally from Tesla. After that, there's a special studies, interconnection studies webinar. There's one on the interconnection process. There's a specific one on commissioning and the process and perspectives from different people in the industry. And then there's a session for IBR registration and reliability standards enhancements. It's kind of the last big technical presentation. And the last one is just, again, kind of a summary, closing out the webinar series and kind of giving next steps. So with that, if there's any questions in the chat, I'll try to pull it up right now. Let me see here. Trying to find a couple of the easy ones. As I'm going through logistic questions, they will be posted on the NERC site, and there'll be a kind of a message going out when those get posted. So let's see. Oh, Andy, you've been answering all the questions here.
Yeah, I answered a few in the chat.
Did you see any that you want to answer? So
here's one. Go ahead.
Oh, yeah, go ahead.
Yeah, go ahead. So there's one that says, do inverter-based resources need synchronous machines online to operate? The answer is yes for conventional wind, solar, and batteries, and the answer is no for grid forming inverter-based resources.
Yeah. And someone also mentioned or asked, they pointed out that modeling disconnect between equipment and actual behavior really needs OEM assistance, and they're having trouble kind of cooperating or coordinating with those folks. Andy, do you have any kind of feedback or high-level feedback for what can be done in those situations, or kind of a best practice from trying to match your equipment to your behavior?
Yeah, I mean, I guess hopefully each manufacturer of inverters will test their individual devices in the lab and make sure that their EMT models and even phasor domain models match the actual hardware devices. One way to help achieve that is by using real code models, meaning actually put the inverter code into the EMT model. Of course, other things like protection should ideally be in there as well if it's a plant level model. That's a quick answer. There you can read whole NERC reports and guidelines on the details of that.
And just to really quickly before I read out the next question for us, what we're going to do after the webinar is we're going to take the Q&A questions, and then we're going to give a kind of FAQ type material piece that comes with the rest of the materials that they get posted. So if we don't cover the questions here, you'll get a written response via that. And then Andy, someone asked if there's, for example, a kV or MVA threshold where EMT studies should be performed for. Is it like a BPS only or 100 kV and above, or something like that?
It's a really good question. I think folks are still trying to figure that out, and it also depends on the specific strength of the grid in the location you're thinking about. One maybe good rule of thumb would be to, at least for larger systems in the megawatt scale, at least collect the models so you have them if you need them, and maybe only conduct detailed studies when the transmission operator feels like that's needed for some kind of stability concern.
Yeah, and just to expand on that quickly, this might be the last question before we sign off for the webinar, but to expand on that, we get that kind of question on this topic and others a lot, right? Where it says, what specific criteria should I be doing X at? And really the answer is, unfortunately, it kind of depends on your region. So if your region has really big issues and maybe load pockets or things like that, that would be something you want to study in detail, and maybe not in detail in other areas of your region. It really comes down to where your specific planning region has issues, and focusing on those issues while also paying attention to the other normal planning things. So yeah, unfortunately, the answer is it depends most of the time. There's no one threshold fits all for everybody. So in order to make sure you're planning sufficiently for your region, you just have to make sure that you understand your region and you're making your criterias accordingly. So with that, we are right at the top of the hour. So thank you, Andy, very much for joining us and presenting on our first webinar series. These will be posted after the webinar series along with the FAQ. And thanks, everyone. And we'll talk to you again on Thursday, same time. Thanks.